Let's directly start into the topic parallel co-simulation. In our context, non-iterative parallel co-simulation. That means simulation steps are not repeated. In this case, submodels are solved independently over predefined time intervals, the so-called coupling steps. Typically, there are loops in the co-simulation. For an example, two submodels A and B, which are bidirectional dependent. To perform a coupling step, each submodel needs the results of the other model to do a step. If we assume both models have the same coupling step size and both are at the same simulation time tk, submodel A, for instance, needs the output information from subsystem B for the next step, but this information is not available yet. There is some kind of a causality problem. To solve this, the inputs have to be estimated. This can be done by extrapolation of the inputs, for example, zero-order hold. That means the last known value is constant for the next coupling step. If the inputs are extrapolated, the needed input information is available and the coupling step for both subsystems can be executed. The results can be exchanged. We can do our next coupling step. Again, extrapolation, execution, and data exchange. What we can see, the submodels can be executed in parallel in different processes or threads. This enables a higher simulation performance in terms of simulation duration, which makes it, for example, more suitable for real-time applications. Nevertheless, we also can see there are differences between the extrapolated signals and the actual one. So there are extrapolation errors which may have an impact on the simulation accuracy. If we assume all subsystems have the same coupling step size, the parallel coupling is quite simple. After each coupling step, all submodels end their coupling step at the same simulation time and can easily exchange the data. If different coupling step sizes are used for the submodels, after a coupling step, the submodel has different simulation progresses. That means they are at different times in the simulation. And the question is now how to synchronize the submodels. We need some kind of synchronization strategy for the data exchange between the submodels. However, why should we use different coupling step sizes when this makes the coupling more complicated? Typically, the coupling step size goes hand in hand with the dynamic of the submodels. That means submodels with a high dynamic has small coupling step sizes and submodels with low dynamic has larger step sizes. If we couple submodels with different dynamics, we could force the low dynamic system to use small step sizes, to have equal step sizes in the coupling. But this will have at least an impact on the performance in terms of simulation duration due to the higher coupling effort. On the other hand, if we set the coupling step size of the high dynamic subsystem to the step size of the low dynamic system, there may be less synchronization between the systems, and this has an impact on the simulation accuracy. Long story short, it makes totally sense to use different coupling step sizes for some applications. A typical parallel scattering for co-simulation is the latest first coupling approach. How does it work? After the initialization of the models, all submodels can start the steps in parallel. The submodels have different coupling step sizes. Let's assume all submodels have a real-time factor of 1. That means 1 second in simulation is 1 second in real time. Then submodel C, with a coupling step size of 1, will finish its step first and has to wait till all other submodels have finished their step. So submodel C is waiting. This is indicated by the red cycle. The green cycles show which submodels are executed currently, and the number within the cycles show the current coupling step of the submodels. After 2 seconds, also model A and D have finished their step and all models are waiting for model B. If all submodels have finished the first step, model C is executed next due to the latest first coupling approach and the smallest simulation progress compared to the other submodels. After the second step of C, model A, C, and D are at the same simulation progress, and so these 3 submodels can perform the next simulation in parallel while model A has to wait. As soon as model A and D have finished the second coupling step at 4 seconds, the models B and C, which are on the same level, can calculate in parallel again, and so on. After 6 seconds, the 4 submodels are all at the same simulation progress and the coupling pattern repeats from the beginning. If we look at the wall clock time, that means to actually use time in real life instead of the simulation time, we can see that there are a lot of white areas between the executed slots in the submodels. These white areas represent the time the submodels have to wait for the synchronization. Compared with the simulation time, we can see that for 6 seconds in simulation, the entire co-simulation takes 12 seconds, despite an assumed real-time factor of 1 for all of the submodels. The simulation takes twice as long due to the scattering of the submodels with different coupling step sizes. The question is, can we do that better? The short answer is yes, with parallel fast scattering. Here we introduce an additional step size, the synchronization step size, which is a global parameter and affects all of the submodels. Based on the synchronization step size, we can define a synchronization condition. This actually means that the synchronization and the data exchange takes place if two or more submodels end their coupling step within the synchronization interval, whereas synchronization interval is the time spent between two synchronization steps. Let's come back for our schematic example now for the parallel fast scheduling and an assumed synchronization step size of 6 seconds. In the first step, all submodels are executed in parallel as before. As soon as the submodel has finished a coupling step, it can immediately start the next step without synchronization. This also applies to the other submodels, so that each submodel can directly execute the next step without waiting for the other submodels. After 6 seconds, all submodels are at the first synchronization interval. The synchronization condition for all submodels is fulfilled and the submodels are exchanging the data. If we now look at the work log time, there are no white areas anymore between the executed steps of the models. There is no waiting time between the submodels. The simulation time is equal to the work log time. That means the real-time factor of the overall co-simulation is 1. This seems too good to be true. There is, due to the higher synchronization steps, less synchronization of the submodels. This brings a benefit for the simulation time, but on the other hand, it decreases simulation accuracy. For a better synchronization accuracy, more data exchange between the submodels is required. That means a smaller synchronization step size has to be used. With, for example, a synchronization step size of 2 seconds, again, in the first step, all submodels are executed in parallel. Due to the small step sizes of submodel C, it can directly start the second coupling without any synchronization. At simulation time 2 seconds, submodel A, C, and D are in the first synchronization interval. They already fulfill the synchronization conditions. Submodel B is still executed, so the submodels have to wait. As soon as submodel B has finished the step, the synchronization between the submodels takes place, and they can all execute again in parallel. At 4 seconds, A, C, and D are at the second synchronization interval. They end their step together and they will exchange the data. In this case, they do not have to wait for submodel B because B will finish the step in the upcoming synchronization interval at 6 seconds. So that means A, C, and D exchange the data and can directly start the next step, and so on. Till all of them has reached the synchronization interval at 6 seconds where all submodels are synchronized, the execution pattern starts from the beginning. The execution of the submodels over the work log time have slightly changed. Simulation duration increased to 7 seconds. That means there is a short time slot where the models has to wait due to the synchronization. If we compare the simulation time over the work log time, we can see that the simulation time takes 7 seconds for 6 seconds in simulation. The green dots illustrates the synchronization points between the submodels. Compared to the system with a synchronization time of 6 seconds, the number of synchronization decreases as well as the simulation duration. That means the synchronization step size has an impact on the simulation duration on the one hand, and then the data exchange and so on the simulation accuracy on the other hand. If we do now a simulation study on an actual co-simulation example with 4 submodels with different step sizes and an assumed real-time factor of 1, where all coupling signals are extrapolated with 0 auto hold and we variate only the synchronization step size, we can compare the extrapolation error and the real-time factor of the overall co-simulation. We will end in a plot like this, where left is the extrapolation error of all coupling signals and right is the real-time factor of the co-simulation over the synchronization step size. For small synchronization step sizes, the real-time factor is around 1, also for a synchronization step size around 6 seconds. In between, it increases up to 1.2. However, it can be shown if the submodels have different real-time factors, the entire co-simulation is dominated by the slowest model and is then almost independent from the synchronization step size. However, the extrapolation error on the other side has an interesting behavior. For small synchronization step size, it is constant. And then the extrapolation error decreases for higher synchronization step sizes. This is against the co-simulation user experience that smaller step sizes delivers worse results than bigger one. The reason is the synchronization condition, where synchronization only takes place if submodels end their coupling step within the synchronization interval. If the step size and so the synchronization interval is too small, there are fewer synchronizations because fewer submodels finish their steps in the same interval. However, if the interval is increased further, it also comes to fewer synchronization due to the larger synchronization intervals. The question is, how can we identify an optimal synchronization step size with respect to the extrapolation error without performing a huge number of simulation runs? Therefore, we need some kind of estimation of the extrapolation errors of the entire co-simulation. Based on our topology of the co-simulation, we can derive the so-called dependency matrix, which describes the dependencies between the several submodels. It includes the number of connections from one submodel to another, but it does not include the information about the step sizes and the scheduling. Therefore, let's consider the impact of the synchronization. During the synchronization of two submodels, the submodels may end at different simulation times. If this is the case, we can directly use the additional information for the next step. That means this part can be interpolated instead of extrapolated. The actual extrapolated part of the submodel results then from one synchronization to the next synchronization step without the interpolated part. So the extrapolated part can be used to estimate the extrapolation error from one subsystem to another in a linear manner. This can be estimated between all submodels and written as a weighting matrix. The weighting matrix can be used to weight the dependency matrix, and based on this, the estimated extrapolation error results as a sum of all of the entries of the weighted dependency matrix. The real-time factor of the entire co-simulation can be estimated by the real-time factor of the several subsystems and their step sizes. The real-time behavior is on the one hand given by the real-time factor of the submodels, so at each coupling step the wall clock time of one submodel is updated by its real-time behavior. During the synchronization of two submodels, the wall clock time of the submodels is defined by the wall clock time of the slowest submodel. Finally, the estimated real-time factor is given by the maximum of the wall clock times over the corresponding simulation time. If we apply the estimation of the real-time factor and the estimation of the extrapolation error to our co-simulation example and compare that to our actual co-simulation behavior, we can see that the estimation behavior, illustrated with solid lines, fits very well to the simulated results, illustrated with dashed lines here. That means based on the estimated extrapolation error, we can determine a step size where the extrapolation error is a minimum. In our example, this is at the value at 2 seconds. Does this really lead to the best results? Therefore, let's consider one coupling signal from submodel A. Here we can see the results from all different synchronization step sizes compared to a monolithic simulation. That means where all submodels are solved in one model with one solver, we can see that none of the results fit to the monolithic simulation. However, there are results which are more close to the monolithic solution. And the closest result here corresponds to the optimal synchronization step size we have determined. If we compare the estimated extrapolation error due to the mean coupling error with respect to the monolithic simulation, we also can see that the smallest error in both cases is at the identified optimal synchronization step size of 2. Let's come to the conclusion. We have introduced a new scheduling approach for parallel co-simulation, the parallel fast scheduling, which is typically faster for submodels with different coupling step sizes by decreasing the number of synchronizations between the submodels. This can be defined by the synchronization step size, which allows some kind of a trade-off between the simulation accuracy and the simulation duration. In addition to that, we have introduced an optimization approach to identify suitable synchronization step size for the parallel fast scheduling. One additional comment. The parallel fast scheduling approach is included in the co-simulation platform ModelConnect, and parts of them are also now available in a new open source project, OpenMCX, which also supports the Modelica standards FMI, SSP, and DCP. Thank you for your attention.